Excellent. Welcome back, everyone, for the keynote session for today. We are so very fortunate to have Dr. Emil Kakkis join us today as our keynote speaker. Dr. Kakkis needs no introduction. However, I will attempt. Dr. Kakkis is best known for his pioneering work developing novel treatments for rare diseases. He is the Chief Executive Officer and founder of Ultragenyx, a company with 4 approved therapies for 5 rare diseases and multiple clinical stage programs. He has won very many awards. I will not name all of them here today, but we are incredibly gratified that he chose to spend his time here today with us this afternoon. His talk today will shed some light on the development of rare disease therapies for neurologic genetic diseases. Dr. Kakkis, the floor is yours.
Thank you. Thank you. Well, I'm certainly happy to be here and happy to be invited by Heidi. Heidi may not know, when she invited me, there was discussion about Stanford, so I thought this was at Stanford and I was going to drive there, and then I found out later it was actually in Utah. But I'm here for the day. And happy to be here and talk about the development of treatments for neurologic genetic diseases. Before I get into the whole talk, listening to everyone today, I had a couple other things I thought I should add on. The first one was, I think the story with Hannah and her doctor's not listening to her. You know, as a physician, when I was in the practicing academic world, I had a secret technique to discover kids with bad problems when I was in the emergency room. And it was the secret technique. I never missed a bad case, and the reason was I always listened to mom. I did. People said, "Why didn't you do this test in the thing?" There was nothing there to see. I said, I listened to the mom. Mom sensed there's something going on, and I'd find these cases because no one else did. So I apologize for the doctors who don't listen to moms, but moms know a lot about what's going on with their kids, and we should pay attention. And so I was sad to hear that people were long off and all that time was lost, right? Time lost, brain lost, and shouldn't be. The second thing is about this whole issue of time loss, which also affects Heidi's family and the other family. This issue of newborn screening, it's getting going, but for this disease, the group of diseases or other diseases, what's taking so long? Why are we still in the 20th century, 1960s kind of way of like PKU mindset? We have all this modern technology, both sequencing and phenotypic, and I agree, Dr. Schultz, you need both. You cannot give up phenotypic screening. The VUS and all that other stuff, we will get better at that. We need to get better, but even without VUSs, you can have mutations you miss. So genetic is not perfect. Together, we should be doing them. We should be doing a much better job, because now there's a whole bunch of diseases that have treatments or treatments are coming. And how could we let families tumble down the lack of diagnosis, lack of treatment, and miss their window, continue to let that happen? That's just not right. And the ACD and other communities that are really affected by it, we need to get together and transform the whole newborn screening approach that we do in this country and resource not just the screening, but the follow-up and how that's done with the proper caliber of professionals that really know their stuff. Because not everyone can call Dr. Longo for every single patient. And Longo will answer the call. I know he does, but it's a lot. So let me talk about development of treatment. So if listen to moms, figure out the diagnosis, then how about treatments? And development treatments for rare diseases, particularly neurologies, have been tough. It's been hard. And what I thought I'd do is take you through sort of some of the history of what's going on in rare disease treatment and how we've gotten to where we are today. And I'll then discuss our program as well on our prodrug for creatine. There's been a lot of discussion of prodrugs, and we'll touch on what we're doing in that area. So these are my disclosure. I'm obviously an employee of Ultragenyx and have stock in the company, all that. But the reason I left academia to go to industry, the reason I went to the dark side is I realized if I really want to treat kids, I have to go where there's enough money so I can move that money into the disease and do what we have to do. And that's what I've been doing my whole career, is putting the money to work and get science, develop rare disease treatments. And there was just no way to do that as an academic, having done a program I'll describe for you shortly. So the development of treatments, new specific treatment strategies are coming around right now, and it's been multiple successful clinical trials treating disease people thought maybe you could never treat. And so it's a really exciting time, but there's still challenges in getting funding. because not everyone believes in ultra-rare diseases and their treatment. Even though the treatment effects can be profound and life-changing, the world right now is like interested in GLP-1s. I mean, how much thinner can we get? Of course, I could use some more, but how much of GLP-1s do we need? How many of those do we have to make, right? I don't know, but we seem to be spending billions of dollars on that, and I think we need to get, the world will come back to what we're doing, but I think that there's a lot of great work now, and the door is open to treating a lot of rare neurologic diseases. But the neurologic diseases in general have been tough because they are hard to access the brain. It's hard to get the brain treatment. There's a lot of irreversible problems. And so the neurology and the assessment of efficacy is challenging. But we have this opportunity to change the future. And so with highly specific precision treatment, we're going to do a lot more for these ultra-rare diseases than we've ever could. And it behooves us to make sure that does happen. So in the early days in ultra-rare genetic diseases, there was a group of people that were working on lysosomal disease. And lysosomal disease had one benefit. They had a mechanism of how you can get the enzyme into cells that you can just put in the bloodstream and it goes there. That biological simplicity said, look, if we could just make some of this enzyme, we can give to the patient. And it led to a whole series of programs. But those programs are important because they established that we can take an ultra-rare disease where there's only a few hundred, few thousand in the world, and we can make a treatment for them. Remember, before that, it was just not happening, right? There's maybe one other treatment, PEG-ADA, that was for adenosine deaminase, but there really wasn't people investing the kind of money required to develop a treatment. But these guys started the science, and then the treatments began. And in my career, from that time to today, I've worked on a lot of different treatments that have been approved, and some are pending for ultra-rare genetic diseases. And we've learned a lot from that. And I'm going to tell you a little about the history of how I started, where we got there, and then we'll get to the creatine transporter deficiency story. So in the early days, we had enzyme replacement therapy. It was one of the first things. It was imperfect, particularly it didn't get to the brain, but we could fix some things. And it led to an understanding I had for this whole treatment strategy is we can't set the standard out the gate, first treatment, that we're going to fix everything immediately, right? If you demand that, you'll end up not getting there. There's no treatments for any other diseases where everything's all fixed immediately after treatment. So why do rare diseases have to achieve that? We start treatment, we get benefit, then we evolve, then we improve. We can't stop at the first one, should keep moving. But after enzyme therapy, then there were other strategies that were often related to these enzyme deficiency disorders. And then they got even more sophisticated with gene therapy, siRNAs, ASOs, and other strategies, which then opened the door to brain treatment because now you could get the drug into the brain compartment through one way or another, and we'll talk about that. A lot of these examples they replace what's missing. And in the creatine disorders, that's sort of true too, but the enzyme or the transporters are more difficult to deliver, but the creatine may be more direct. We learned a lot about biochemistry and all this, and that kind of helps us understand what we have to achieve and how to determine that we have been successful. So my first program was working on, as an academic professor at UCLA. I know Dr. Longo's heard the story maybe like 5 times, but I have the bungalow. I just want you to know that it was the equivalent of being born a poor orphan in research. I've worked in that World War II era bungalow, and we were working on a treatment, and it's a struggle. How do you develop a treatment? You got one tech and part-time showing up, and how do you develop an enzyme therapy? We did, and we ended up successful getting there, and it's a very long story. I remember when we first gave a first dose, as a kid named Ryan, his parents started a foundation called the Ryan Foundation, and they raised money and gave it to me in the lab. I was happy to get it, but it's also pressure. I got to do something. We got to get there, and you don't even know if you can. So it's a challenge to step forward to something impossible. But the truth is, parents know it's impossible too, but we're in it together. And someone was talking to me just a moment ago, I think it's very true. The fact that someone shows up to try to treat is a huge win, right? That someone cares and we're working it. But everyone knows it's hard, but we finally got the enzyme made, and you can see his parents, Mark and Jean, are very happy. He was very unhappy because he was in a trial and they poking him and giving him tests, and all day long he was not happy. But it's so funny how happy they were and how annoyed he was. So, but as time went on, the story, that was 20 years now on enzyme therapy. He grew up, got a driver's license, graduated high school, graduated college, and then I was present when he got engaged, and then I went to his wedding. That's a possibility. Treated him early enough. He still was physically affected, but it was early enough that he could actually grow up. And that should give you a vision of what we can be doing if we start early, find the diagnosis, and start doing these treatments. Well, that's Ryan. That was my first story. I wrote a book because there was something that happened in that story, which is the struggle of development of an academic without enough money. And then you follow it with a lot of questions and issues with the FDA and the drug development process, which is not designed for ultra-rare. So I had to write a book. I also started a foundation. There was a lot of pain and suffering in there, even though there was success. And my hope and career has been ever changed toward trying to fix that so we get more of these done and have less suffering to get there. So one other example I put forth is the MPS 7. I put this forth because it was our attempt to demonstrate that even a very rare disease could get treated and developed. Slice syndrome, there's only right now about 21 kids in the United States, and there's a treatment approved for them. And we took it on because we knew it would work, but because I also want to set the standard that you could do this, that you could do a 3-patient dosing study and a 12-patient pivotal trial and get approved. But it's been a challenge, but this was attempting to open the door to really ultra-rare diseases, and there's a lot of them out there, by the way. That treatment's been approved, and it's being treating kids around the world with MPS 7. So the problem, of course, with those enzyme therapies, they don't get to the brain, and we need to get to the brain for a lot of diseases. And the MPS diseases do have brain disease. There are some. MPS 1 severe patients have brain disease. MPS 7 patients have some brain disease. So a lot of these disorders do have it, but we haven't been able to solve it. We fixed some of the physical problems, so we went back to look at the brain. And we started doing some work with the Ryan Foundation, actually the patient group funding this work, and in my lab, and we figured out maybe we just put some enzyme in the spinal fluid that goes around your brain. What if we put a whole bunch in there? Can we, without avoiding dealing with the blood-brain barrier, can we get that? If we put enough enzyme, could we push enough of it into the brain? It turns out that works. And we did get enzyme in the brain, and then there's been a number of trials now using that approach, but it led to one treatment for a severe genetic brain disease called infantile-Batten's disease. In that disease, they have very aggressive neurological problems, seizure, developmental delay, very bad disease, and it's very fast. Like within 2 or 3 years, they go from symptoms to complete devastation. And if you give that enzyme in the spinal fluid, then you can stop that decline. You can see the blue line on the top. That's what the treated patients did, and the red line is what happens from the natural history of this disease. This is one of the first approved therapies for the brain, right, for a very bad disease, but it showed it was possible that we can open the door to doing treatment of brain diseases. And maybe it was crude, we're just putting the enzyme in the spinal fluid, but a general rule I also have in rare disease drug development is first make it work, and then make it easy, right? Parents want something that works, and then we'll deal with easy when we get there. Let's get to because if you try to solve all the problems, you end up solving none. So we solved that one. Now, lately, the things have gotten better for neurologic disease, and we're working on a treatment for Sanfilippo syndrome. In this case, there's an enzyme deficient in this disease in the brain. They can't metabolize this glycosaminoglycan, and so they build up this sugar in their brain. It injures their brain, and they end up having it's like Alzheimer's disease, but in a child, right? Maybe diagnosed at age 2 to 6, and they may be bedridden by the time they're 10 or 12 years old, and take 5 or 10 years in that state before they die. It's a horrible disease. And in this case, we need to get the enzyme in the brain. And the way we did it was in a gene therapy, an AAV gene therapy. And that gene therapy vector, we put it in the bloodstream, and that AAV9 will get across the blood-brain barrier a little bit. Not a lot, but a little bit. But it turns out if some neurons and other cells get the gene, they'll make extra enzyme, and they secrete it. And the secreted enzyme then will cross-correct the other cells. So you don't need a lot, and this is where the gene therapy plus knowing the biology allows this to work. This treatment now is under review by FDA. Our hope is to get approved later in the year. There's a whole bunch of families with samples. I'm getting like emails like daily. Just got another one yesterday. Everyone's waiting. It's urgent, and they're waiting for the FDA to say go, and I am too. But this will be the first treatment ever for a Sanfilippo type disease, and those parents have been waiting for a long time. They formed a lot of foundations, raised a lot of money, had seen so many things stopped. So this will be the first one. It shows, the gene therapy shows we can stabilize their development so they continue to gain ground over many years, even up to, we have about 8-9 years of treatment data. And if not, they turn the corner and they decline on the normal trajectory of this disease. So we're pretty excited about that drug and hoping to see an FDA approval, which will be amazing for all the families out there waiting to finally get it. And one of the cases just came up was diagnosed by genetic screening. One of the gene sequencing programs actually found an MPS IIIA patient, just happened. And so we'll be able to treat that kid. See, that will be like, there's what the future looks like, right? Some screening, and by the way, I think it should be phenotypic and genetic, but screening found at a very young age and now treated. That's the way the world should work for Sanfilippo. So what about creatine transporter? So you may not know, but in 2011, I was talking with Lumos and the leader of Lumos at that time about cyclocreatine. But when I looked at cyclocreatine, in my mind, it didn't look like a good choice because the energy of creatine didn't look right. And we conceived at that time, this is 2011, of making a prodrug for creatine. Now, how do you treat what's going on in creatine transporter? And we've had some discussion about it, I know, so far. We know there's not enough creatine in neurons, and we know the neurons, there is synthetic sensitive creatine, but the neurons and the blood-brain barrier don't have transporter, right? The transporter is on the neurons and on the blood-brain barrier. So if creatine's around outside the neurons, that's not any good either. It has to get in the neurons. And even if the glia are making it, they're not getting enough in. So the question is, how do you solve that problem? Now, gene therapy is one way people think about it, but we have to hit the blood-brain barrier, and we actually have to hit all the neurons. And so this is a hard thing to do, actually, to hit every neuron and to actually do it efficiently with safety, because you have to give a very high dose of gene therapy vectors. Our view was that was so hard, and this was 2011, there actually wasn't any CNS gene therapy to that time. We thought, but what if we know that creatine replacement and GAMT and the others can be really transformative, so can we make a version, and I think we've already had a couple talks about prodrugs, so maybe you've heard it already. Can we make a version of creatine? Now, I will talk through a little bit about the disorder and our view of it, but then I'll get you I didn't put all the chemistry, how we made it and all that, but I realized I should have. But you guys are apparently a glutton for chemistry punishment, and I can give you, I just thought, well, I'm not going to tell everyone about the chemistry, but maybe I should have, I don't know. But here, let me talk about creatine transfer a little bit. I'll give you a little background. We'll get to our molecule, then we can talk about how we got there with it. So I try to simplify what creatine is doing. It has many functions, but because Longo will immediately correct me, I'm sure. It has many functions, but the main function is a store of energy, but I like to think of it as like a battery. It's a battery in the sense that your body is taking ATP, that's the energy it normally has, and it's storing energy in creatine phosphate. It charges it up, puts on its charge. And why is it doing that? Well, because it can't store it as ATP safely, so it puts a whole bunch in. But your brain, unlike other parts of your body, need to have bursts of energy in use. It has to be at a drop of a hat. You don't have time to metabolize glucose and make ATP. You need the energy now, right? Like an electric car, you want to push the pedal and it goes, right? Your brain has that same kind of response. It needs a fast energy response. So your creatine acts as a battery. So what happens when you don't have it is the neurons fire and they need like a immediate energy kick, and they don't get it, right? So they run low, and then they get into trouble, and then things are not working the way they should. And so what's happening in this disease, and we don't have enough of the batteries to hold charge. We need to get this battery in there so that the cells can now charge it with phosphate and have that energy source waiting and able to deal with the surge that these kids' brains need. So that's sort of the way I'd certainly look at it in the simplest way. So in creatine sufficiency, the brain is able to have all the energy it needs. In creatine deficiency, they don't have it. Now, you can have a creatine deficiency because you don't make them, creatine, or because you don't get it to the brain with a transport deficiency. There's certainly two different ways. Now, if you look at on the left side here, in creatine synthesis disorders, you can give creatine, and giving it early obviously is really important, but if you give it early, you can flood the system, get enough in and have a transport and get the brain to have enough creatine. It's still crude, you're giving a lot of it, and and that it's not beautiful, but it works, right? Gets it in, gets it done. In transport, you don't have that, and so we had to come up with a better way of doing it. And I understand many people understand what the problem is. The creatine itself is hydrophilic. It likes water. It doesn't like membranes. We have to get it to go across the blood-brain barrier, but also across the neuron into the neuron cytoplasm. So we started working on a creatine transporter. Now, let me get here. So I'll tell you now a little about the chemistry of what we did. We've actually made hundreds of creatine molecules, and I would say the project, which has been going on for 15 years, has gone through at least 3 dark nights of, I call them dark nights of research. That's when you think there's no hope and there's no way we're going to solve this problem, and the program's not going to make it, right? One of the first came when we first started trying to make these prodrugs, is that the creatine would cyclize and become creatinine in a drop of a hat like that. You make the chemistry, you put it in, boom, becomes creatinine. Because the nitrogen on the creatine cyclizes to the carboxyl group, makes a circle, and that's creatinine, that's the waste product. And so every time you put something on those molecules to make it like more hydrophobic, more oil or fat soluble, it would immediately cyclize. We went through that for like a couple years. We couldn't get that straight. And then we figured out about making a cycle. Now, the reason the cycle has an advantage is when you make a cycle, it's set up because the second cleavage is harder to make than the first. And what ends up happening, but if you cleave the first one, it's still a hydrophobic molecule. The second cleavage, that nitrogen cleavage, that's for this very specific enzyme that's in the neuron cytoplasm. So there's designs that the second cleavage is supposed to occur in the neuron, not elsewhere. The esterase part, it can be cleaved a lot of places. So it's designed to clip in a sequence, one first, then the other. And the last one, when it comes off, it's meant to be in the neuron. So we were excited. We had this idea. But it turned out we were making molecules that had to be stable, right? And we found out we made them stable, they get to the brain beautifully, but then they wouldn't metabolize. They wouldn't get cleaved because they were so stable. And we had to change the whole approach to drug development to realize, well, we want them stable, but not too stable. So we got rid of all the screening technology that people normally do for drug development. We said, get rid of all that. We're just going right to animals. And we took molecules we thought were not that stable, but they were stable enough to go in the circulation. And then in the neuron, they would actually get clipped and they would be opened. Because you can't just deliver the prodrug, you have to deliver free creatine, right? And I think that was part of the discussions I was hearing. And we did a lot of work to show that we are delivering free creatine, and we've isolated and shown that creatine is in the neuron cytoplasm. And so the prodrug we've made through a lot of tests, trial and error, is basically given orally, and it absorbs through the fat system. It ends up in circulation, gets to the brain within minutes, very fast. It doesn't last in the circulation that long. It gets to the brain very fast in minutes. In the minutes, it becomes creatine pretty quickly in the neurons. So we're using LC mass spec to prove, by using LC mass spec, we know if it's prodrug or if it's creatine, right? We can tell. It's D3 labeled, so it's labeled with a deuterium. And we can also, through oscillation and other methods, show the creatine is actually in the neuronal cytoplasm. So that's all the work we did. And so all the questions you asked were all good questions. We've done that work over the time to get to a molecule that actually does what it's supposed to do. And I call it a double trigger prodrug. I don't think the team likes that name, but it's kind of a cool ring thing, and it has 2 steps. There's no prodrug ever done like this before, but it has a reason why it looks the way it looks. And the work that they've done has been exceptional. But getting through the creatinine thing, getting through a too stable, not working thing, and then we had a problem, how do you give it, IV or oral? And we ended up doing oral, turned out to be way better and way safer. So 3 dark nights, we thought the program was on the end of canceling, and then came back. Exciting. And the truth is, the research is hard. And every time you think you're down, sometimes it takes one more idea, and then you're up again. So that's the prodrug we made. And I'm going to give you a highlight of just a few experiments, not all of them, because I didn't think you wanted to watch a lot of data slides. But here's one data slide. We use the creatine transporter, the CTD rat. We did the rat because it has a bigger brain. It's a little easier to do analyses of the rat brain because it's bigger than a mouse brain. So the rat, unfortunately, doesn't really have that much phenotype, though. So you can't really do a lot of clinical studies of it, but we can use it pharmacologically to show, did we get creatine where it needs to go? What we show you here is if one day, if you continue to dose and go over time, you accumulate more and more creatine. And a good question that was asked was, well, how much creatine do you need, right? How much do you need? Well, it looks to us like we could get close to a millimolar if you allow it to go. We've done it in non-human primates and in rats. We can get up there, but it takes time. It may take a couple months of daily dosing before you get up there, but it builds each day, right? So we think normally when you look at an MRI scan of a kid's brain, a normal brain, they would have 5 millimolar or something like that, people will say. But the 5 millimolar is all the creatinine. It's not necessarily in the neuron creatinine. And our belief is, if we're doing this, we're talking about neuronal delivery, and it's not everywhere, that we think you don't probably need as much. How much? I don't know. But neurology is a threshold-driven business. Our hope is that you get enough in, you'll get there. We think this should be enough. We think we're in the range where you should be enough. But that'll be one of the things we're going to figure out in the trial, how much you have to give and how long does it go to get their brain built up with enough creatine, enough batteries to make it work. And I actually think some will be better than none, more may be better than some, and we'll have to work through that in the clinical program. So we were able to show that, for example, that it was creatine. We've done it through just LC mass spec of tissue specimens, but this one was kind of cool because this is you take a rat brain section. A normal rat brain is, you can see that bright colors, this is a MALDI-TOF. Someone said MALDI-TOF earlier, and probably not a common term here, but it's a way of chemically looking at the individual molecules, and we can show free creatine. So normal brain, that's what it looks like when you cut it and look for creatine in pixels across. In the CTD rat, you see, and you do the same experiment, like there's no creatine, right, in the brain? And then on the right is what happens when you use our molecule, the prodrug, and you can see that's free creatine coming from the brain. You can see how it's mapping to where the brain, the neurons are, and where the gray matter is. So that one piece of evidence. We've done this in non-human primates and others, but we feel comfortable getting in neurons, and we're getting metabolism to creatine. Now, another question I think that was asked was, well, how do you know it's being used with phosphate, right? That was the question, it's getting utilized? And it's very hard to do that experiment in a whole brain. We did this experiment in vitro with neurons, and what we're able to show you is that if we put the prodrug in that situation, it will become creatine, and we can show now that the ATP levels rise in the cell and the ADP levels. So it's kind of maybe tricky to explain, but if you look at that bottom right, the ADP correlation, the little purple on the left, that's where the untreated animals are. Their ATP is low and their ADP is low. That's because your body gets rid of ADP if you don't have much ATP, right? They're trying to keep it in balance. You lose both. But you need both, but you lose both because your body's trying to equalize them so whatever you have as energy can work. When we treat them, you can see the rats move up. Their ATP goes up and their ADP goes up. And on the left, you can see how much the ATP goes up. So they get more ATP than ADP, which means we're loading up and we're changing the energetics of the cell, right? So That change in energy says that the presence of creatine is allowing these neurons now to build up and have more ATP. They're not running out of energy. They're able to sustain the energetic state of the cell. This gave us confidence that we're going to do it from an energetic standpoint, what we need to do to treat these patients' brains. There have been some other experiments of this type, but this is the one I thought was maybe the easiest to understand. So where are we right now? Where the company's focus this year has been on finishing the CMC, the chemistry manufacturing controls. That's called CMC. That's the FDA jargon for how do you make it, right? But we have to give it to a child, so we can't just take a powdered chemical. We have to figure out a formulation that they can take, that they won't be bitter and cause kids to, have a problem with it, vomit or something. So we've been designing, scaling up the manufacturing and the formulation. In the monkeys, we had some issue with them, vomiting, right? Like the drug, it needed some sweetness to it that helped stop that, manage the dosing. But this is kind of standard drug development stuff. So we'll fix the formulation. We've been doing that, and we're pretty far along now. So we'll have a formulation that we can figure out the dissolvable type tablet thing, which we'll be able to use for kids or swallowed potentially. So that's the CMC part, making the drug, and that's in progress and should be finished this year. On the other side is, what about the clinical side? Well, there have been a number of things going on that are very valuable. The creatine registry, of course, the endpoint program, which is very important for this disease area, and also the vigilance study, which we acquired from Lumos and completed. But that gives us 3-4 years of study to tell the FDA what you all know, which is they don't get better on their own. And you might wonder, why would the FDA think that? But I've gone in there and they said, well, I see them getting better, but how do I know they wouldn't get better on their own? And I had Dr. Munsford with me in one of those meetings, who's MPS doc, I think Dr. Longo knows. He said, they've never gotten better. I've never seen a patient better. How can you say they got better on their own? But the truth is they want to see data to show they don't get better on their own. And here's the data now. For 3-4 years, they don't get better. So if we make them better, people will know. Now, that doesn't mean we won't have to do a controlled study, but I will tell you we probably will. But we're going to come up with the most efficient plan for doing that. But all the studies, registry, outcomes, and developing the endpoints are real important, which I think is most exciting lately, particularly about the endpoint story, is that there are some good stories now for neurologic kids, developmentally affected kids, that are actually in the middle of, school age or older kids that actually have improvement. And we were just hearing about some news today from Taisha on Rett syndrome, showing those kids can gain ground with a gene therapy. We have been studying Angelman syndrome, which is a developmental delay seizure disorder, kids 4 to 17. And we show those kids brains can start developing. They've been not developing since they were like 2, and they can start gaining skills. They can start thinking. They can start understanding language that they didn't understand, and their motor function improves. And that was even 15, 16, 17-year-olds that we've studied, 4 to 17. And we thought maybe only the young would respond, but all of them respond. So any of the theories that older patients can't respond, well, let's try it out, right? And we owe it to parents to do it. We did try it out. It turned out, well, they do get better. And everyone knows, okay, it's not going to be, nothing will be perfect. We know, right? You know, I don't have to explain it to you. But you want to see something better for your kids, right? Those angel kids are getting better. And so fortunately, we didn't just study the ones that people thought based on the mouse studies. We studied the range. And now we're broadening the range. We're studying adults and everybody, because we're going to open the door to anyone that wants to see. Then we'll have to see. And there may be some patients that don't respond, or maybe they can't. But why not take the chance? Let's see what happens. And let parents and doctors make decisions for their patients, what's enough or what's not enough. But I've been really impressed that the neurologic disorders where you have neurons, they're not neurodegenerative, but the neurons are there, that you can get them to turn on and they're plastic enough in their connections and other things to start functioning. And for Angelman, we had kids who had never spoken a word in their life who speak several dozen words, who didn't understand a 1 or 2-step command, an oral command. You could tell them stop, they didn't understand. And now they understand language. Imagine for a parent being able to tell their kid some simple things that now understand what you're talking about. And the kids get calmer because now they understand what's happening. So imagine what happens when you don't understand anything that's happening around you, what that's like, right? Very, very challenging. And the kids will get frustrated, and they're frustrated in their behavior. They say they're being aggressive. So when I hear the aggressive thing, well, they're probably frustrated, or they're not sleeping, or other things are going on. And if you or I were in that situation like that, we'd be doing the same thing, right? And so we cannot blame them for that situation. It's because their body is not receiving the signals it needs to know what's happening around them and what's going on. So to see that happening has been quite expressive. So I don't know what's going to happen in creatine transporter. I don't know. But there's possibilities here. We're going to find out. And the key is, can we get enough creatine in? Right? Can we get it in? Can we get it in safely? And can we get in the quantities that are going to make a difference? And will the biology help us? And will the patients turn on? We will see. So where are we going right now in the trials? Finishing making the product. And the first step in the clinical trial process, I think someone earlier in their talk talked about clinical trial process, is a phase 1 trial. Now, because this is a new chemical entity, like a new drug compound that never existed before, it's often better to do normal volunteer studies for phase 1. That's what FDA expects. You might think, who's a volunteer taking these chemicals? Well, there are volunteers that take this. It's not dangerous to take this compound if you have creatine. It doesn't, but by doing it with a normal volunteer study, we can get it done faster, more inexpensively at a special unit, and we don't have to expose patients to this until we figure out what's the safety look like, what dose range is okay. Of course, you never try to dose we harm anyone, but we'll gingerly work through the dose schedule, trying a little more, and see if we can get to where we think we need to be able to treat patients. That's phase 1. That's what's coming, and we're getting that designed and put together. Once that's done, then we would go to a phase 2A type study, which is, now let's treat a few patients with creatine transport deficiency. I saw the questions, like, where is this trial going to be? We don't have a design where it is exactly, or the inclusion-exclusion exactly. Because we'll have treated normal volunteers of a wide range of ages in there, we will likely be able to go to children, probably not very young children, but older children. That study I would expect to be a multi-dose study. We'd start low, we might titrate them up. We'll do probably the MR spectroscopy to try to see if we can measure creatine and see if we're having an effect. We just don't know if that method is going to be sensitive enough, but we'll hope is in a very limited number of centers, we'll try that. If we're seeing something, we get it right, then we can expand the study, add more centers, and then treat some more patients if we get a handle that we're doing something when we get from the first few patients. And then we get into what we call phase 2-3, where we start expanding and adding more groups. Will it have a control group? I would bet it may need to have a control group, an untreated group. How long it will be, I don't know, but I'm guessing for this type of thing, generally the FDA prefers it. However, the control group, if they don't get drug, initially, when they cross over, they'll get it. So they'll still get access before anyone else, and so there's a value being in the study is to help us figure this out. And then you get access to the treatment before anyone else. So that's the phase 2-3. I expect that we'll be looking at multiple different domains. We've been working with FDA on Angelman to stop thinking about one symptom as defining a disease. And you have that same problem in creatine transporter. Like, people say, what's the most important symptom? Like, well, you're not going to treat one thing. Did you come here for one thing? Well, there's a whole bunch of things. So why are we picking one? Where did that come from? Well, that came from statisticians. And I say, let's leave the statisticians over there for a second. Let's talk clinically. What are the top 5 or 6 things, right? You would say, let's pick the 5 or 6 things that are important to me, that are going on in my kid, and let's look at those together and make a decision. Is this helping? Because some kids have some problems, some kids have other problems. And if you only limit to certain problems, that means you only include kids that have that problem and not the other kids that don't have that problem. What does that tell you? It only tells you about a slice of the population, not everybody. We've been developing a method called the multi-domain responder index. Don't need to know about it. Basically, we're looking at 5 domains in Angelman, 5 different domains: cognition, receptive communication, sleep, behavior, and motor function, right? It's a nice grouping of different problems that are really important, and we're scoring people if they have a clinically important improvement or not. It's also a very powerful technique for variable diseases. The FDA we're still teaching the FDA. They are allowed it to be part of our plan. If the trial, which will unblind later this year for Angelman, looks very good, my hope is we get them to start accepting that approach going forward for neurologic diseases that are heterogeneous, which will allow us then to enroll a broader array of patients instead of selecting people with a variety of manifestations and allow kids to benefit or respond where they can. That's an important part of, I think, getting past the single endpoint thing. And what I tell people, when you go to the doctor, like you have a problem, would it be odd for him to say, what's your one symptom? No, don't give me 5, I want 1, and I'll treat that one symptom, right? It makes no sense, right? So we're gonna measure 5 things, 5 domains of function, capture what it looks like, and it's a very powerful method. My hope with the Angelman, it'll open the door and we'll be able to use that for the creatine transport efficiency. We do have someone from our EDS team, Tricia is here. Her job is to figure out what those domains will be and how to measure them. That's a tough job. Now, we've been doing those studies. Those are the prep studies. But I'll tell you one thing about drug development. You may participate in all the things that we think we know, but when we get in to start treating kids, we're going to learn more, right? The way you really learn about disease is starting to treat them. When you start to treat them, you learn way more about what's going on that you didn't understand before until you start the treatment. So our hope is that we'll learn from that and continue to adapt the methods in the early part of the phase 2 study. So when we get to phase 2-3, we'll have a really good plan to help demonstrate the efficacy and the safety. So those are the 2 there. So in summary, we're getting there. It's been 15 years. I don't even know how that happened. When I thought back, I thought, oh my God, how could it be 15 years? Honestly, I think we should have gotten here 2-3 years earlier. We were close before. The financial world, the markets, the things, all these things conspired to stop us. We've been working on 20 diseases at once, so, but we're here, and now we are partnering with ACD, and Heidi and I have signed an agreement in which we're going to a venture philanthropy agreement, which ACD will provide over the coming period $4 million, and that we would then use that to help get the trials going. It also allows me to have a responsibility for actually executing those trials, right? So that's a little heat on us. This is okay, right? Right? And helps you make it more feasible to get there quicker. If the trial is successful, then the ACD will get a return on their investment. When the drug gets approved, they'll get money back, and then that money you guys can use to do more treatments or better other things, right? And we've done agreements with Angelman. It was a little bit different because they made the drug, actually, but the money we provide back to them, they're doing other treatments, right? So this is a healthy collaboration where you're helping us, we're going to make things go, that will help you, and honestly, we're committed, just as you are, to see these patients get a treatment. And hopefully this prodrug that we spent so many years and so many dark nights on is there, and that we've got the science right, and we've done all the thinking we need. So I want to thank all the CTD families who've been in the Vigilance study and all the other endpoint studies. There's ACD, of course, and Heidi for coming here today. And the UX 068 team, that's the code name at the company, 068. Obviously, that relates to the SLC transporter number if you didn't get that already. But and I want to especially thank Marcus Andrews and Arjun, who've been to the people on this program for a lot of years, living and breathing it, going through the dark nights and thinking hard, and they came up with some really great solutions to get us here. And there have been a lot of team, because so many years, a lot of team members are part of it. I thank all of them, because it's not just me, it's all these people doing everything to bring you, hopefully, a treatment which it's the beginning, guys, but we have at least the belief that this is going to be a good replacement treatment strategy using a novel prodrug for creatine transport efficiency. So thank you for having me, and I'm open to any questions.
How about that? Another stronger round of applause. We have exciting times ahead. Lots of luck to us. All of us gathered here. This is a moment of hope. Several dreams hopefully coming to fruition in the next couple years. All right. Questions?
Hi, thank you for your talk. I really admire your heart for rare disease patients. One question on, I guess, drug development plan, because I saw that there will be clinical efficacy pivotal studies separately. If we can get MRS to be more accurate and consistent across, could it be used as a surrogate endpoint to expedite the approval process? If not, can that multi-domain index be validated through Angelman syndrome trial?
Yeah, so the question of how to get approval, the FDA will constantly say, oh, we believe in biomarkers, we want, to approve them. But then when you get in the room and you're having that discussion, they go, well, yeah, but what's your proof of this, that it's predictive? And the proof they want to predictive is almost would require us to do the full development program, then come back and say, now you can prove it. Well, at that point, it's too late. We already did it. The challenge has been they've not been that accommodating, and I will say I've been doing, my whole book talks about this very topic, and that biomarker, by the way, was pretty straightforward. That was an easy one. I couldn't get that through. I couldn't get them to accept it for MPS 7 either. Those were easy ones. This one's going to be even harder because they're going to say, well, how do you prove that your MRS signal is enough if you don't have anything going on? So what I'd say to you, we have not, in our heads, believed that we're going to be able to use the biomarker approach. The problem we have, and we had with Angelman in thinking too, is, well, what if it takes a long time for seeing benefit? Then maybe the trial won't be plausible, right? It won't take too long. Well, the thing that's encouraging both for Rett syndrome lately and for Angelman, two other diseases where there's not neurodegeneration, neurons are there, but they're not working because of a problem, is that the response was actually in weeks to months. So people said, I need a biomarker for Angelman. I said, well, if they respond in weeks to months, then we can use that response, right? And so our hope in creatine transport will be like Angelman. That is, there's something going on in weeks to months that we can capture in a controlled study to be able to show, so that a study is only 6 months, but not, let's say, longer than a year, hopefully, that range, like Angelman, and be able to show clinically. I believe that's the best way forward. I think validating MR spectroscopy by this method right now, I'd say this whole study might get us there, but I will say one thing about it. It's not the best method. Like, it's precision and accuracy. It requires highly trained, controlled, and you can't even cross centers sometimes because of the methodology. The problem I have is this. It could be that you don't see a peak there, but you have 300 micromolar, 350, 500 micromolar. It's not showing a peak, but the patient's better, right? So with biomarkers, I like the biomarker to be more sensitive than clinical, so we can tell what's going on. But I'm not sure in this case that that's true. That actually could be the clinical will be more responsive than the biomarker, and the biomarker may not help you. In other diseases, for example, the biomarkers are super sensitive, even to a subtherapeutic dose. So that it helps us know what's going on. So we're going to do MR spectroscopy. That's actually here in the backup, this here. We're going to do it. I don't even know if it's going to be the right answer yet either. But we're going to do it because it's there, and we'll see. We'll see. But I have a feeling, my gut tells me it's not sensitive enough, and that maybe if clinical responds, we'll just stick to clinical. And then we use the MDRI to gain the power. So even if the changes are not huge, but their patients are and they're heterogeneous, we can capture improvements in 2 or 3 domains here, 2 or 3 domains here, a couple domains in the other kids, and you pool that together and show this is the totality of this is that they're getting better. Does that make sense? So that's how the MDRI can help us get more power out of a clinical endpoint study, and that may help us get to where we have to go. That's my take right now. I may be wrong by the way, as I said, we do the trial and then we learn. And it could turn out that thing is amazingly sensitive and really good. But right now, I would say clinical is the way.
Yes, first I want to thank you and your team for pushing through all these obstacles and all these challenges. Speaking for me and my family, it means the world to us. Second question is, what can I do with my kids, whether individually or through the Association of Creatine Deficiencies? What can we do to help? Like, what part can we play?
Well, there'll be a point in time where we're going to try and enroll studies. So I think the one way is to enroll in studies. The other is if there's any natural history studies been done, but if there's any other, we may need to studies to look at outcome instruments. This might be something that that Tricia might be doing, which is having patients test out some methods with us, right? So they have to come and let us test out some methods to see how good they are, how sensitive they are. Those are some things. So those are a couple things I can think of right now. It might be the ACD needs help to continue to raise funds and support ACD and what they're doing. We have a set amount we're doing, but I think that may be a third thing that I would say. But participate in studies, any endpoint at development experiments we need to do, you might be able to help us. Some of that could be even an online burden of illness survey we might have. I'm not sure if we've done it, but I haven't talked with Tricia about all this, but burden of illness stuff we often do online, so you could just even participate in that, where we try to get as many people as we can to tell us how they rate things, what's important to them. And that's part of the patient voice. We like to get it early on. We've been doing it with the natural history, but we'll need more. So those are places where you could step up and tell us stuff. And sometimes it gets tedious, and I appreciate I've had a lot of disease areas where they say, everyone keeps asking us this. I keep doing it again. I've asked for patience for asking again, but let's do it one more time. But we have a very good team of PhDs, experts in the development of endpoints. And so their work can help us craft validated clinical endpoints that we can get FDA to accept. So that's why it's so important.
First of all, I just want to thank you for being here today. You've been amazing. And I don't know if you all heard that. That's amazing. $4 million from the ACG to Ultragenyx. That's incredible. So I think everyone... So I'm a parent of a 14-year-old with CTD. He wasn't diagnosed till age 10. So thank you for acknowledging CTD, like supplementation, working in older children and adults, and including them in your study, because we were worried that we would be left out. And my son has made amazing improvements with the creatine supplementation. So it's been life-changing. But when your study says, like in phase 2, it said, older children, adults. It said that they can't have any creatine. Is that like?
Yes, to be in the study, they probably couldn't be on creatine because it would complicate our interpretation of what's going on. And we know there have been some CTD patients. You must be on a lot of it, I'm guessing, right? Like a massive amount, because I've seen some of the papers on it. And you get a massive amount, you get a little in. See, those papers actually give me hope because not a lot going in, but they still get better, right? So that tells me if we get a little in this way, they might get better, but it might be easier taking, a gram instead of many grams a day, right? But you couldn't be, I don't think you'd be, if you're on creatine, it would cause a problem. So this is going to be a tough decision. See, this is why you asked what I'm going to ask people to do. I may have to ask them not to be taking creatine while they're in the trial. And that's a hard give, right? Especially if you're going to end up in a control group. And we just had this issue with our osteogenesis imperfecta program. It was tough for kids to give up stuff they had. And honestly, you might wonder, why are we doing placebo still? I get it. It just becomes proof. Everyone seems to want that, It's not just them. It's like people from your insurance and other people want it. But the key question is, how long does the trial have to be? How long do I have to hold out, right? So if instead of a year, if the patients respond fast enough and we can make it 6 months, right? That will help, right? So my hope is they respond enough in 6 months that we can see the measurement and we don't have to keep them on placebo for a year. FDA made us do a year for Angelman because 6 months probably was enough, but we opted for the year. That program was a lot more complicated though, and there's a reason from a safety standpoint why we had to do that. This one, maybe not. So yes, you have to get off creatine to be in it, but let's try to make it as palatable as possible. But I appreciate you bringing that up. It's a really important point, actually. Other questions?
Hi, everyone. I'm a parent of a child who has gamed.
So you're back there, okay.
What is that? Can you hear me?
I hear. I just was looking for where you were physically.
Okay. So first of all, I would like to thank ACD and your team for doing such a hard work on the CTD side. My question is, in all of your research and studies, have you come across the impact of this enzyme therapy on the GAMT? And from all the knowledge you have worked in all these years, what is your feeling on the effect of these therapies on the GAMT? And do you have any plan down the road on bringing GAMT in as part of your
Right.
studies and therapy? Thank you.
Okay, so the question is, could a creatine prodrug be useful in GAMT, right, where you're flooding the system trying to get some across? It could be potentially. We don't have a plan yet. I think it is something that's come up. Would a more efficient delivery mechanism help? It could. The thing is, a creatine is pretty inexpensive compared to other drugs and that we have all this development on, but it may be that it's not sufficient. So maybe there's some people who could do better and we should try it. So we'll keep that as an idea. I think we have to figure out if it works in creatine transporter, but could it help in GAMT? It's possible, but I think we have to keep that as an item to be looked at some point. I think the biggest problem in GAMT is patients got to start too late. That's the hard part, and the question is, that part may not be fixable or whatever injuries happen, but is there insufficient delivery of the creatine? Could this help? That would be the question you could try. And maybe at some point, if we get this going for creatine transporter, that we can think about doing a pilot study in patients with GAMT who are not getting like the best effect or not optimal or having tolerability issues, and could this help? But let's get to the first step first before we go wide. Question over here.
I have one right here.
Yes.
First, I want to say thank you. I know in most of the studies that they're usually geared to the male populations, and there's not much for females. Will the study that you're looking at conducting be eligible for females, and especially adult females with CTD?
Yes, we'd want to consider both females and males. We wouldn't have a restriction because there's females that have significant disease, and I think even in we have another program with CDKL5 deficiency is an X-linked disease also, where it's all females, right? So I think we would include females. How we handle it, I think, is a question, but we would expect to use females. Would we use adults? I think in the phase 2A, there would be adults. Would they be in the phase 2-3? I think it might depend, but we're not ignoring adults. We will make sure we manage them, whether in the phase 2-3 or in some other study. We'd want to see what happens in adults over long-term therapy. So in the phase 2, in general, I expect us to look at a broad array of patients to see what's working, how it looks, and then we'll probably figure out what's going to be the phase 2-3 study that we can do, hopefully a shorter study and get that done. But we often have secondary studies that are open label studies that will look at other types. For example, in Angelman, we did 4 to 17 in the main pivotal study. But we opened another study called Aurora that has adult treatment access, little kid access. The ones that are not in the phase 3, they're in that trial, and other genotypes, like unusual genotypes. We put a study there. So we give them a place to get access and for us to learn. But it may not be in the main study. That study will figure out from phase 2A who are the best patients to go in what we call the pivotal study. All right, so that's what we're doing in Angelman. So the adults above 17 are in that study, and the main study is in 4 to 17. In the history, usually we've been able to get the drug labeled for all of that because we can prove the drug works in one population, but we'll show it works in the others. But we don't have to do another randomized study to prove it. We've already proven the cause and effect relationship of the drug and the outcome. So we just look, does the other patients have an effect that's important? Is it safe? And that data can help support, including the full age range. So with us, we'd probably do something similar in this program as well.
So, Dr. Kakkis, we have one more question here in the corner, on the left.
Oh, yes.
Yeah, just very quickly before this question, quick time check for parents who need to pick their children up from camp. You will need to leave at 4:30 to pick your children up from the camp. And now we'll get to the question.
Hi, thank you. I was a bit surprised at the complexity of your clinical trial design. And I guess, but you spoke to it, I had a similar question about the surrogate endpoint. I'm wondering if you see any changes in this FDA with all the talk of real-world evidence studies and such, and helping push things through, if you've actually seen that in practice, or it's all just optics. is my first question. My second question is, when you think about your phase 1 and you think about dosing design, are you looking at different dosing schedules that could potentially tease out whether it's a bioavailability issue or an enzyme kinetics issue, talking about transporter in the brain?
Yes. Well, what we'll be doing is in the single ascending dose and multi-ascending dose, the phase 1 study, we'll get a handle on how fast the prodrug disappears, how fast, we'll from that phase 1 study, we'll get an idea of what the dosing is. From our expectations in non-human primates, so in monkeys that we've treated, that if you give the drug orally to them, they actually get a very interesting pattern. It appears that the drug may be like entering their GI tract and then released slowly. So the PK in the bloodstream is actually steady state. It's flat after a few days, right? It reaches steady state. So we'll be able to look at that steady state and see how it relates to what it was in non-human primates and whether that concentration is what we'd expect. But the beauty of that is we think you don't have to dose more than once a day, and what we're doing is topping up what's in the stomach, and you get that steady state. We'll be able to use the pharmacokinetics to figure that out, if that concentration is what we think. And the brain, we're using the MR spectroscopy to look at concentrations. I'm not sure the CSF is going to give us an answer that would be interpretable, right? Because what you see in the CSF, is it reflecting what's going on in neurons always? I'm not sure. So we'll have to rely on what we've learned in the monkey studies to show that the drug gets metabolized and what concentrations give us delivery. And we'll look to see in that phase 1 study, are we getting concentrations in the bloodstream that should be adequate to deliver to the brain in humans. Now, in the human study, when we do the phase 2A study, we're going to look at their blood levels too, right? So we'll get the same kind of information to see, is it replicating? And if we can reach a reasonable steady state, then our hope would be that what it's doing is the prodrug is being leaked from the GI tract to the brain every hour continuously, and the brain is accumulating creatine steadily. So the hope would be that if we hit enough concentration, that should be enough drug. But I think you brought up the point of how much is enough, right? Yeah, I think in your talk. But I think that's definitely a difficult question. How much is enough? We don't know. We're going to hopefully find out. You're talking about the phase 2A study? Yeah, so as a habit, Ultragenyx, we don't do primary endpoints in phase 2A because we have to make a guesswork of what that primary should be and then fail the study if it doesn't hit. So our approach to phase 2A is, instead of putting ourselves in a box, we'll look at 5 or 6 endpoints, we'll look at PK and PD, and we'll make a call. We're not going to try to get approval off that study. We need to learn first. So it's called the learn, confirm strategy. So we'll learn. We'll see what responds, what doesn't. We'll get the PK, PD, is it being metabolized, is it working, and what's improving. And from that, we'll then design what phase 2-3 should be like, where we actually test out, and we'll pick a primary, which we need I need a primary from the FDA standpoint. My hope the primary will be an MDRI primary, which means 5 domains assessed together. But we will do an MDRI-like endpoint in there. We will be looking at it, and we'll probably look at 5 or 6 domains as the key ones. And we need your help in helping us decide what are those 5 or 6 things are probably the top group of things that you hope for, that we want to make sure we're evaluating carefully. Hopefully it's not going to get too complicated, but oh, the real world evidence thing. Yeah, I haven't seen any real world evidence that real world evidence is actually going to be used for anything. But there's so much talk about it. But I'll tell you, for rare, not a chance. What real world evidence they're talking about is cardiac outcomes in 500,000 people. Okay, real world evidence, that's what they want it for. There's not enough interest in it for us. So whenever we try to use, let's say, open label study, long-term treatment data, it's always a battle. I've not seen it well accepted, in spite of the fact that I think it's actually very valuable. But so far, I haven't seen. I think the FDA is under a lot of change, by the way. The regime has changed, and so there's things happening. I think they're being flexible in some rare disease programs, and I think my hope is that the changes it'll be better. But solving this with real world evidence, I think, is going to be hard. I think in rare, there's just not enough patients out there to compel the FDA to believe anything, right? They like huge numbers of thousands and thousands of patients in a thing. That's what gets them moved.
Sorry, one last question.
Yes.
Because you mentioned that there will be different endpoints for 2A. Would you be measuring similar endpoints that you'll be using for the pivotal study, or
Oh,
it
yeah.
will be completely different?
Oh yeah, we always pilot everything we're doing pivotal in the phase 2A. It's actually a rule of the company. You don't study in phase 2-3 what you didn't study in phase 2. You got to study it. So we'll have phase 2A, we'll have a lot more endpoints probably. In phase 3, we'll have fewer. We'll narrow it down to what we think is working. So we'll test out everything, and Tricia is your torturer over there. She's going to be designing all these things that you're going to have to go through in phase 2. Sorry, Tricia, I meant it with kindness, but her job is to figure out what's that palette of things, and it'll be asking a lot of very painful, repeated questions about things, and hopefully a few functional tests and other things, but I don't have enough depth of knowledge where she's at on it, but I'm guessing it'll be a lot of stuff in phase 2A. We good? Thank you.